definition of a rational expression. It is an algebraic fraction with polynomials as the numerator and denominator. Okay. Actually, I suppose I had space for the definition down there, but oh well. Okay. So some examples. Okay, it's going to look like a fraction. And in the numerator and in the denominator, we're going to have polynomials. So we might have, I don't know, x squared plus 1 over 2x minus 5. That is a rational expression.
I'm getting like flashbacks to the last unit now.
Yes. Well, so we're going to, like the first unit?
Yeah.
Oh, no. OK. Well, hopefully they're good flashbacks.
Well, they're just memories.
OK. Good. OK, so that's one example. You could even have something like this, 3 over x. Technically, that is also a rational expression because the numerator is sort of like a polynomial with degree 0, if it's just a number, because x to the 0 is 1. And then the denominator is definitely a polynomial. It's actually a monomial, but still fits the definition of polynomial. OK? All right, let's maybe do one more. I don't know. That one. That's also a rational expression. OK, here's another one. That's also a rational expression. OK? Non-permissible value. So we just actually touched on this without me actually saying those words. But a non-permissible value is any value of the variable that would make the overall expression undefined. Now, when you're thinking about a fraction, those are division. We just talked about this. What can we not divide by? 0. Right. Okay. So the non-permissible values are whatever x value is going to make the denominator 0. Because when we divide by 0, we have an undefined number. Do you guys know why that is, by the way? Why can we not divide by 0? Yeah.
Yeah, you can't really have 0 groups or something.
Yeah, so that's, I kind of explain this 3 different ways depending on who my audience is, right? So yeah, so if you think like back to when people were learning about division, you have 5 cookies, you divide them amongst 2 people, everyone gets 2.5 cookies. If you have 5 cookies, you divide them amongst 0 people, where do the cookies go? They have to go somewhere, but there's nowhere for them to go. Okay, so that problem becomes confusing. At around this level, I'm going to go do this on another page, actually. And this sort of junior high up to grade 10 or 11, I would say, OK, well, we know that multiplication and division are opposite operations. So if I say something like 3 times 5 equals 15, there are 2 corresponding division statements that must also be true. 15 divided by 5 equals 3, and 15 divided by 3 equals 5. OK? So if we were to suppose that we can take a number, I'm just going to actually do it this way. We can take a number, let's say, I don't know, a, and divide it by 0. And we get a number, some number. If this is true, then this must also be true. The number times 0 must equal a, right? So think about this. 15 divided by 3, well, that means that also 3 times 5 equals 15, right? So if this number exists, where we could divide another number by 0 and we get a number, a real number, then this must also be true. Take a number, you multiply it by 0, and you get a number. That's not true, because 0 times anything is always 0. So this is impossible. Therefore, this does not exist. Okay? So that's one reason. The other reason, and this is getting a little bit higher up, is if we look at what happens when we try and divide by 0, not by 0, but by numbers close to 0. Okay? Think about taking the number 1 and dividing it by a really, really small amount. You get a bigger number, yeah. Right? So if you take 1, if you think of this, this is a relation, and we haven't gotten into this, but essentially we're getting into something where this number is 1 over another number. So if we look at numbers here where this is really close to 0, graphically, right? So let's just first know, okay, if x is 1, y would be 1 over 1, which is 1. If x is 2, y would be 1 over 2, which is a half. Right? If x is 3, y would be 1 over 3, which is a third. So that's sort of what's happening. But if I get close to 0, 1 over, let's say, 0.1, that's 10. 1 over 0.01 is 100. 1 over 0.001 is 1,000. So these numbers are going to shoot up that way. That's going to be the shape of the curve. Okay? That is what happens when I get close to 0 from the positive side of the x-axis. The value of 1 over that number actually approaches infinity. Okay? Now, what happens, though, if I go from the negative side? If my number is -1, -2, -3, well, what's 1 over -1? -1. So here, y would be -1. What's 1 over -2? 1 over -2? -0.5, yeah, -0.5. So this would be over here. 1 over -3 is -1/3. This would be over here. Okay, now 1 over 0.1 was 10. What's 1 over -0.1? -10, right? So now instead of going up this way, from this direction, they're going to shoot downwards.
Oh, it's one of these ones.
Yeah. So what's happening in the graph actually, as we get close to 0 from the right, our values go up towards infinity. And as we go close to 0 from the left, our values go down towards -infinity. And we get this divergence. And when there is divergence, we cannot define what this would be.
It's so weird.
Yeah. So this is a much higher level way of thinking about it. And I want to go there with you just because I think you guys can understand it, but I wouldn't expect you to come up with that or even to support an answer with
Oh,
that.
I've never thought about it as like dividing something by a small decimal. Mm-hmm. That does make a lot more sense now.
That's good. This is actually the calculus explanation. There we go. We're getting a preview of that. OK, so let's go back to this. Non-permissible value is any value in the expression that makes, of the variable rather, in the expression that makes the whole thing undefined. Well, that's going to happen in division when the denominator is 0. So if we're looking, for example, at 3 over x minus 4, okay, what would x have to be here so that x minus 4 equals 0? What minus 4 is 0? 4. Yeah. So the non-permissible value here, the NPV, is that x cannot equal 4. Okay? Now let's say I had something like this. 5 over x squared plus 5x. And I want to know what value of x would make that denominator 0. Okay? Yes?
1.
Well, 1 squared plus 5 times 1 is actually 6. Okay? So it's kind of hard to see in this format. This is a binomial. What did we just learn about in our last unit when we were looking at polynomials? What process were we doing? Yeah? Factoring. So let's try factoring this. What's the GCF there? X. And then we're left with x plus 5. Okay? So you have to think, okay, the denominator can be factored into 2 factors. If you multiply 2 numbers together and the answer is 0, one of those 2 things must be 0. So let's suppose this factor is 0. If this factor is 0, what would x be? 0. So that's one non-permissible value. It can't equal 0, because if that guy's 0, we'd have 0 times 5, which is 0. What if this factor was 0? What plus 5 equals 0? Negative 5. So it can't equal 0 or negative 5. Okay? And in general, the number of non-permissible values that you are going to have kind of depends on the number of factors that you have in the denominator, with the exception that if you have repeated factors, like a perfect square trinomial, for example, you're not going to say the same non-permissible value twice. Okay? But each factor has the potential to create a new non-permissible value. And so when we are working with rational expressions, one of the expectations is that you are stating the non-permissible values as you go through your work. Okay? Now, I actually, before we get into this, I want to talk about this too, because it's interesting. Let's go on to the next page. Again. So you guys last year looked a little bit at linear functions, or linear relations, I should say. Do you know what that graph looks like? Y equals x.
Isn't it just a line?
It is a line. What does it look like?
Y is equal to x.
So when x is 1, what's y?
1.
1. When x is 2?
This is diagonal.
Yeah, it's a diagonal. When x is negative 1, y is negative 1. So this is what it looks like. Okay? Let's consider this. Okay, so looking at this rational expression, what would the non-permissible value be? 0. X cannot equal 0. Okay, now does this simplify? X squared over x? What is x squared over x equal to? Okay, so it's going to look like that, but when x equals 0, there's actually a hole in the graph. Okay, so I'll show you, even if you do this graphically, and we're not getting into this now. We're going to learn more about the graphing calculator next unit. But I just want to show you, even if you're using technology, when you put in x equals 0 into that equation, you are going to get an undefined value. So I'm going to put in y equals x squared over x divided by x. I'm going to graph that. Okay, so there it is. That's what it looks like. But I can, let's see what will happen if I trace it. Yeah, so when I trace it, you can see, okay, my x value is 0. It's not giving me a y value. It won't, the calculator will not compute that. Because when the calculator is computing it, it's saying, okay, y equals 0 squared over 0. You can't divide by 0. So it will not show up as a value. The hole is so tiny, though, that it looks like there's no hole there at all, right? Because any other point, either greater than 0 or less than 0, would be defined, but not when x equals 0. Okay? So I just kind of think those are fun. We're not going to look too much into those, though, but I just thought it's interesting to consider the difference between this and this.
It would be like infinitely small.
Oh, yeah.
Like you would not ever be, oh my, that's
It's so small.
weird. I don't,
Yeah.
oh,
There's
so
a hole there. It's actually, it's called a point of discontinuity, a hole or a point of discontinuity, because technically, anywhere where the graph is discontinuous is when you have to lift your pen off the page to draw the graph. So technically, you would have to lift your pen off the page just for a whatever, not even a millisecond, to put that hole in and then continue. Okay? So anyway, I just think that that's kind of neat. All right, but let's keep talking about non-permissible values. Okay? So let's just do a couple of examples. Let's take a look at this. X minus 3 over 23. What would the non-permissible values be here?
3.
Okay, so think about this. What value of x makes the denominator 0?
26.
If any? Denominator is 23. Just 23, that's it.
Oh, it's fine, because no matter what,
Yeah.
it's only if x is in your if your variable's in your denominator. That's
Right.
when you start like panicking, going, oh.
Yeah.
wait,
This will never be 0. Doesn't matter what x is. This is 23 is always equal to 23. So this has none. Okay? If we look at the reciprocal, though, 23 over x minus 3, that is going to have a non-permissible value,
Which is 3.
which is 3. Yeah, so x cannot equal 3 here. Okay? Let's look at this guy, 2x plus 1 over x squared plus 1. Okay, so when you're looking at non-permissible values, you only really need to consider the denominator. Okay, so let's think about this. What value of x would make x squared plus 1 0? Yeah?
-1x.
Okay, so if x is negative 1, negative 1 squared is 1 plus 1.
Right, okay.
Yeah, so I can see you're nodding your head. There are none.
Oh,
Because this has to be greater than or equal to 0. And then you're going plus 1. So the smallest value that this will have is 1. If x is 0, the denominator will be 1. If x is anything else, it will just go up from there. Yeah. You're going to get this must be positive. A positive number plus 1 is a positive number. Yeah.
Is there a point to determine the non-permissible value other than like just for funsies?
Okay, so is there a point to say it other than just for funsies? So the answer is yes, and it has to do more with what we're looking at here. Because when, we're going to look at rational expressions now, and actually it's a 20-1 thing. And we're going to look at, this is called a rational function, okay, because it's, or rational relation. Relation is when you have two variables and there's an equal sign in them. So there actually is graphically a difference between these two. And anytime you have a value of x that makes it undefined, if you turn that into an equation with y, then what's going to happen is you are going to get a point of discontinuity in your graph. And that's kind of a big deal when you start looking at other pieces of these graphs. Now, unfortunately, you guys haven't learned too much about graphing yet, right? You've learned about plotting points. You maybe learned about taking an equation and making a table of values and then using that table of values to plot the graph. But you're just sort of on the edge of what you're going to learn about equations and graphing, because what we're going to start to do starting in grade 10 is actually look at different types of equations that all behave the same way and generalize them, right? And that's kind of what you do for grade 10, 11, and 12. In grade 10, we just focus on linear relations that form a line. And then in grade 11, you're going to look at quadratic equations that form a parabola, and perhaps some other types of equations, right? And then once you do all of that, then you might study calculus, where things like points of discontinuity in a graph become really important. So yeah, it's a really valid question. And I hate saying to you guys, yeah, it seems like we're just doing it for fun now, but there are reasons for it later on. Yeah. OK. All right, so this guy actually here does not have any non-permissible values. OK? Let's look at this guy, 2x plus 1 over x squared minus 4. There's two of them. What are they?
I was going to say, what I meant was
Oh, it's 2. OK. There's 2 of them, though. Yes. What's the other one?
the other one is negative.
Yeah. So if you think about factoring this, this is a difference of squares. Right? So from this factor, the value of x that would make this 0 is negative 2. So x cannot equal negative 2. From this factor, x cannot equal 2.
That's so weird. Like, not weird, but like interesting. So.
I think so too. OK, so I want you guys to practice this. So do these couple questions. There's 5 of them. And all I want you to do at this point is to state the non-permissible values. And as a hint, if you don't know what to do, try factoring. See if you can factor the denominator. OK, so simplifying fractions. Let's say I have, I don't know, 21 over 30, which is a fraction. OK? Is this in simplest form? No. OK, so what would the simplest form be here? Yeah. 7 over 10. That's right. OK. Now, many of you can do that in your head. But what's actually happening that you don't even think about anymore is you're actually considering factors of the numerator and factors of the denominator. And are there equal factors that can cancel? So what's kind of going on in between, it's almost like prime factorization. You're going, OK, 21 over 30. Well, 21 is 3 times 7. And 30 is 3 times 10, and 10 is 2 times 5. So it's 3 times 2 times 5. OK? And then the common factor of 3 cancels because 3 over 3 is 1. And you end up with 7 over 2 times 5, which is 7 over 10. So your brain just does that right now because you've been doing it for so long. OK? But with rational expressions, we don't always have the luxury of being like, what's a factor of this polynomial? And what are the factors of this polynomial? And working that all out in our heads. So when something is written in simplest form, either a fraction or a rational expression, it's when the numerator and denominator have no common factors other than 1. Right? So 7 over 10, the only common factor of 7 and 10 is 1. So that is fully simplified. Okay? Now, when we're looking at an algebraic fraction, a rational expression, we have to factor the numerator and factor the denominator so that we can get a feel for what are the factors of the numerator and denominator. And then if there are common factors, we can cancel them. Okay, so that's kind of the process that we're going to take here. Now, this guy over here, all we have really here is a monomial over a monomial. So although this is a rational expression, it's a very simple one. When you just have a monomial over a monomial, you can really just apply your exponent laws to simplify it. Okay? So you could think, okay, well, 15 over 30 is 1 over 2. And then a squared over a cubed. So two of them will cancel, and there's 1 left in the denominator. And b cubed over b, one of them will cancel, and there'll be 2 left in the denominator. Okay? But what's really going on if we think about expansion is 15 is 3 times 5 times a squared times b times b times b, b cubed. And in the denominator, 30 we already did was 2 times 3 times 5. Okay, and then times a times a times a times b. And then we just cancel all of the common factors, right? So a pair of 3's cancel, a pair of 5's cancel, 2 pairs of a's, and 1 b. And then if you look at what's left in the numerator, everything has canceled except for b times b, which is b squared. And in the denominator, I have a 2 and an a. Okay, so you've already kind of done a little bit of this when we looked at our exponent laws. Now, one thing, though, is that non-permissible values always apply to the original expression. And so if you cancel out something that would lead to a non-permissible value, you have to state those at the beginning before you start canceling. This can be a colorful hallway sometimes. Okay. So lots and lots and lots of action in this hallway. Okay, so if I look at all of these, I have 2 different variables. So I have to state the non-permissible values for each one. What value of a would make this would make the denominator 0? 0. So a cannot equal 0. And what value of b would make the denominator 0? 0 for the original one. Okay, so those are my non-permissible values, but this is my simplified expression. And if you take this simplified expression along with these non-permissible values, it is equivalent to the original. Okay, we've already seen how the difference between x and x squared over x. There's one tiny difference, and that is that x squared over x has a non-permissible value. So you do have to state that before you simplify. Okay, let's try this guy. So there's quite a bit of factoring to do here. In the numerator, we have a trinomial. So how can we factor this? Yep. Yeah, so there is a common factor 4. So I'm going to take that out first. And then in the denominator, there's a GCF of 2. Yeah. OK. Am I done yet? No, because the numerator factors further, right? So here I'm looking for the a value is 1, so that's kind of nice. Looking for 2 numbers that multiply to negative 21 and add to negative 4. What are they? Yeah, it's negative 7 and 3. So one of the factors will be x minus 7. The other one will be x plus 3. And then here's my denominator, over 2 times x minus 7. OK, so firstly, before we have the fun of crossing stuff out, what's the non-permissible value or values here? What value of x would make this undefined?
7 and negative 3.
OK, so 7 and negative 3. Is a fraction with a numerator of 0 undefined?
It's not.
No. Right? 0 over 10 is just 0. So you can have 0 in the numerator. That's fine. You cannot have 0 in the denominator. So here, x cannot equal 7. Okay, but once we write that down, oh, there's some common factors. So that is common. And 4 over 2 is 2. So what we're left with is 2 times x plus 3. Okay, questions with that? All right, so I would like you guys to just practice these 8 questions. And I think we'll leave it there. Oh, I do want to talk about. Oh, no, there was one other. Okay, I knew I had to talk about something else. There's one more. I lied. We're going to do one more, and then you guys can work on these guys. Okay. So 2x minus 6 over 9 minus 3x. Okay, so numerator. How can I factor the numerator? This is like 3. There's GCF of 2. And what about in the denominator? GCF of 3, okay? And I'm left with 3 minus x. Okay. So firstly, non-permissible values. 3 minus what equals 0? 3. So here, x cannot equal 3. Okay, now, do I have any common factors that I can cancel?
Technically, yes, but you need to do the thing where you factor out the negative number.
That's right, yeah. So not exactly, right? Because x minus 3 does not equal 3 minus x. But what could we say about those two numbers? Yeah.
The only difference is their sign.
The only difference is their sign. Yes. The only difference is their sign. So if you think about 3 minus 1, that's 2. 1 minus 3 is negative 2. 3 minus 5 is negative 2. 5 minus 3 is 2, right? 3 minus 100 is negative 97. 100 minus 3 is 97. So if you think about that over itself, what's 2 over negative 2? Negative 1. What's 97 over negative 97? Negative 1, yeah. So it doesn't matter what x is. This will cancel and become negative 1. So you can cancel that and replace it with a negative 1. That's one option. And then what you're going to get is negative 2/3. Okay, but really, mathematically, what's going on is if you start with this, okay, what I'm going to do is I'm going to factor a negative 1 out of this factor. So I'm not going to do anything with the numerator. But if I take out, instead of a 3, I take out a negative 3, then I have to think about what would be left. So negative 3 times negative 3 equals 9. And negative 3 times positive x is negative 3x. And now the factors are identical. And so when I cancel them, I get 2 over negative 3, which is the same as negative 2/3. Okay? And you can do it either way. When you start to do this a lot, which to be honest, you're not going to start to do this a lot really until grade 11 and 12, you'll start to see that a lot where you have a binomial factor over itself and its subtraction in the order of the terms is reversed. And when you start to see that, you'll be like, oh yeah, that cancels to make negative 1, right? And it just becomes a little bit more efficient if you do it that way. But mathematically, what's going on is we're factoring out a negative 1, okay? And then the factors are identical. Okay, now I promise I'm done. So I want you guys to try these guys. I want you to state the non-permissible values as well.